Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I see there are a whole bunch of questions saved up or sent in from our submission form. So let me see what I can do with these. And I think our theme for these Q&As about science and technology is ask questions that you've kind of always wondered about the answer, but they seem too somehow too simple to actually ask. I'll try to answer them. Not sure if I'll be able to. All right, Universe Within asks, could the expansion of the universe affect biological evolution? It's an interesting question. The first question, I suppose, is, does the expansion of the universe affect the conditions here on Earth? And the answer is, certainly at the beginning of the universe started very small at the Big Bang and very hot, and its expansion is what caused the universe to cool down and the force of gravity to be able to form things like galaxies and stars and so on. So in that sense, the very existence of the Earth owes itself to the expansion of the universe. But if we ask about the universe as it is today, and does its expansion affect life on Earth and evolution on Earth? I think that's a more tenuous question. For example, here's something that the expansion of the universe probably affects, which is the fact that the night sky is dark. Because if you imagine, if the universe, for example, was, you kind of look out in a certain direction in the universe, and the question is what you see a star, or is there no star, or at least no star that's reasonably bright? And it's partly because of the expansion of the universe. There are several different effects that contribute to the night sky being dark. One is the universe is finite. There's only a limited number of stars you could even ever see going as you look sort of out to the edge of the universe, so to speak. Another is that gravity clumps stars together. So instead of having this kind of uniform shell of stars at a certain distance out, stars are clumped in galaxies and clusters of galaxies and so on. And the third is that the very fact that the universe is expanding means that stars that are further away have the light from those stars is shifted so that it's in effect less, well, it's redshifted. It's shifted from something that looks like the white light of the sun to something that's redder and redder and redder and redder and redder. And when you reach sort of the edge of the universe, it's been so shifted that it's actually no longer visible light, it's microwaves that have a very low frequency. So I don't know to what extent evolution of life on Earth is affected by the fact that there are these cycles of light and dark. We could certainly imagine being on a planet where one face of the planet is locked towards a star, and the other face is away from the star. For example, Mercury, closest planet to the sun, has that feature with respect to the sun. One side of Mercury is constantly locked so that it's facing the sun and the other is facing away. Just as the moon, as it circles the Earth, it's locked so that we always see the same side of the moon and the far side of the moon is away from us. That kind of locking occurs because the moon is, although it's made of rock, it's slightly deformable, and the deformations of the moon over time cause it to kind of, they're sort of tidal deformations. They pull out in one direction and squash down in the other direction. As that happens over time, it will gradually lock the moon's rotation to be such that it's synchronized with the Earth in such a way that it keeps one face towards the Earth. But I don't know whether if there was a planet that if our Earth had been tidally locked so that one side of it was always in light and one side of it was always in dark, would that have fundamentally affected biological evolution? I'm not sure. There's one effect that perhaps we can think of as being somewhat of cosmological origin, and that's the preponderance of right-handed molecules in biochemistry over left-handed ones. So when you make a biochemical molecule like sugar, for example, if you look at the arrangement of atoms, you can have kind of a sequence of atoms where you can have the same atoms, but it's as if you're kind of curling the set of atoms around like your left hand with one atom sticking out like your thumb, or you're curling around the other way so that those same atoms are curled around like your right hand with the thumb sticking up. So there are two different chiralities, two different handednesses that are possible for something like sugar, glucose. Those, if you just sort of throw the atoms together to make sugar, you'll get equal numbers of left and right-handed sugar molecules. But somehow biological life doesn't work that way. Biological life always makes right-handed sugar molecules. And in a sense, by the time you've got sort of life that's always making right-handed molecules, the processes by which it makes new molecules will tend to always lead those molecules to be right-handed rather than left-handed ones. By the way, for most people, if you eat left-handed sugar, most people find left-handed sugar doesn't taste sweet. So there are the chemical reactions on our tongues that lead to taste are affected by whether they're right or left-handed molecules. But when we just sort of throw the atoms together to make molecules, it doesn't give us more right-handed than left-handed molecules. So that's something sort of special to life. So the question is, why did we wind up with right-handed rather than left-handed molecules in life? And it could be that that's just a pure sort of accident of history. And once there were a little bit more right-handers than left-handers, so to speak, and this is, I'm talking about molecules, not at the level of actual handedness of us and the way that our brains are laid out. It could be that that's a sort of a slight preponderance of right-handed molecules, and then those ones were able to interact more easily with right-handed ones, and so the left-handed ones kind of lost the game. But there's a question of, can we derive the fact that it's mostly right-handed molecules and that they got the advantage? And maybe the answer is yes. And I think one theory of that is that when there are certain processes where sort of handedness matters. So most of the time, if you were to just take pictures of, billiard balls bouncing off each other, or for that matter, atoms bouncing off each other, most of the time you would kind of take those pictures and you would be able to say, here's the picture, and now let's invert the coordinates. So let's take everything which was going left to right, make it go right to left, invert everything. The picture that you get from inverting everything would look just as convincing, just as plausible as the picture you get without inverting things. In other words, sort of as far as the basic laws of physics are concerned, it seems as if everything is invariant with respect to inverting the directions of space. So that's sort of in the first approximation, that's what's true. Now, it turns out in the mid-1950s, it was discovered that that isn't always true. There are subtle effects where you can tell the difference between kind of the inverted version and the non-inverted version, and one occurs sort of in the physics of the Earth, so to speak, and here, and the other does not. So the particular phenomenon where that was first identified is radioactive beta decay. So that's something that happens in nuclei that sort of have too many neutrons relative to protons. What will happen is, and sometimes the other way around as well, but that's like different phenomenon. But basically, you'll emit an electron as a neutrino, and your neutron will turn into a proton. So that happens, for example, if you just stuff too many neutrons to go along with a single proton, they'll decay away by emitting electrons and turning into protons and so on. Okay, so in any case, that phenomenon, you can ask the following question. You have a nucleus that's decaying by emitting an electron. There's sort of a question of whether, if you make the nucleus spin in a certain direction, will the electrons be emitted? Will they care which direction the nucleus is spinning in terms of which way they go? Why does that matter? Well, the point is that when you are looking at kind of a top spinning, and you look at a top spinning and you look at it in a mirror, let's see how to think this through. Essentially, the sort of spinning of things where there's an axis and a rotation doesn't invert in a mirror the same way that just pure directions of things invert. So a fancy mathematical way to say it is there are vectors, which are kind of like just motion of things, and there are so-called axial vectors, which are things that represent an axis with rotation. Axis with rotation doesn't invert in the way that pure vectors, pure directions invert. So if you're asking the question, does everything sort of invert the same way? If it matters which way things are spinning, then you don't get the same inversion. Let's be more specific. Let's say we're dealing with a particular kind of particle. Let's pick a neutrino, slightly obscure particle, but relevant for these purposes. As a neutrino goes along, it's going in a certain direction. The neutrino is also spinning. It's on its axis. And the question is, how is the direction in which the neutrino is going aligned with the direction that the neutrino is spinning in? And the thing that was implicitly discovered in the mid-1950s and then clarified a little bit later is that neutrinos are always kind of left-handed. When if you look at the direction of their spin relative to the direction of their motion, it always forms kind of a left-handed thing with the thumb representing the motion and the fingers curling around the direction of the spin. And that means that as you sort of work that through, the end result of all of that is it matters because in beta decay, neutrinos are emitted, neutrinos are always left-handed. To compensate for that, the electrons end up having a certain handedness, or the distribution of where the electrons come out relative to the spin of the nucleus is affected. Anyway, a variety of different ways to say it. But the end result is that in radioactive beta decay, the electrons that are emitted tend to always have, is it right-handed or left-handed? I'm not sure. Maybe they're right-handed to compensate for the left-handedness in the neutrino. I'm not sure. But anyway, so when the electrons come out, there's sort of a difference between, there's more right-handed ones in the sense that their direction of spin is, let's say, anti-aligned with the direction of motion, and less left-handed ones. So what? Well, the hypothesis would be that there is radioactive beta decay that occurred on the early Earth. And the reason for that is because carbon-14 is produced. So carbon is usually carbon-12. That means it's a carbon atom with 6 protons and 6 neutrons, so a total of 12 particles in the nucleus. But there's also a version of carbon, carbon-14, that has an extra 2 neutrons, and carbon-14 decays through beta decay. And carbon-14 is produced by cosmic rays that come from particles from the sun, and so that's produced in the atmosphere of the early Earth. You get carbon-14, it decays. The electrons in the carbon-14 decay are preferentially a particular handedness. The fact that those electrons that are just sort of hanging out on the early Earth tend to be preferentially of a particular handedness, then the theory goes, that affects the chemical reactions that occur, and it tips the balance a little bit in the direction of having right-handed sugar rather than left-handed sugar. That's a hypothesis for how things get to be sort of right-handed rather than left-handed, and it's a way in which, well, not quite cosmology, but at least astrophysics affects an aspect that's been burnt into the evolution of life on Earth. It's a general question, the extent to which things like spins of particles and so on affect chemistry. Mostly in chemistry, it's just a question of where did the electron go, not, or maybe how does an electron interact with another electron, but not sort of how does, particularly when it comes to nuclei and so on, doesn't usually matter to chemistry which way the spin of a nucleus goes. But there's some hypothesis that a few phenomena, like, for example, famously, the magnetic field sensing apparatus of pigeons might be making use of the interaction of spins of particles with things. So a rather long answer, and I think the basic answer is that I don't know of really good connections between the cosmology of things and the evolution of life on Earth. Let's see. So question here, how much does the sky weigh? How much does the Earth weigh? Well, what does weigh mean? Weigh is how much force is there as a result of gravity when pulling something that you've got down towards the center of the Earth. So weight is usually defined as something that depends on the force with which gravity is pulling on something. But that force is proportional to the mass of the object. What is the mass? A mass of an object is usually defined in terms of, if you push the object with a certain force, how much will it accelerate? Newton's second law says force equals mass times acceleration. So the amount of acceleration is proportional to the force divided by the mass of the object. The heavier the object, the harder you're going to have to push it to get it to accelerate a certain amount. That's the so-called inertial mass of an object, is what determines how much sort of resistance to starting motion there is. Now, it turns out, basic fact about physics is that the inertial masses of objects, also that the mass quantity that appears in that characteristic of inertia, is also the same quantity that appears in determining how much gravitational force there will be on an object. The force of gravity is proportional to the mass of one object. The force of gravity between two objects is the mass of one object multiplied by the mass of the other object, and then divided by the distance squared and multiplied by the gravitational constant. But that gives you the force between those two objects. And it's a fact, so-called equivalence principle, that says that the inertial mass of an object, the resistance to acceleration, is the same mass that appears in the gravitational mass. And that is what determines that gravitational mass is what determines the weight, the amount of gravitational force that pulls an object towards the center of the Earth. Now, if you say, how much does the Earth weigh? In common language, we'll typically mean we could mean both what's the force of gravity pulling on something to say what does it weigh, and what's the mass of the thing, because those are mathematically equivalent, or it's physically equivalent. So, but when we talk about weight of things on the Earth, we usually mean how much does the Earth pull on the thing. So for example, if we took the thing to the moon, where the gravity at the surface is 1/6 the gravity on the surface of the Earth, then we'd say the thing weighs 1/6 as much, even though the mass of the object would be the same. So when we ask how much does the Earth weigh, that's kind of a funny question. It probably, what we really mean is what's the mass of the Earth, and is something perfectly well defined. The mass of the Earth is what determines both the inertial, the way that the Earth its motion is affected by forces and so on, and also the amount of gravity that the Earth feels, say, from the sun, and that the moon, for example, feels from the Earth. So can we work out what the mass of the Earth is? Well, let's see. Can we do that? I don't immediately remember the mass of the Earth. I actually vaguely remember it's 10 to the 26 kilograms, but that might be wrong. Let's work it out. Okay, so the Earth, the radius of the Earth is, let's see, its equatorial circumference is about 24,000 miles. So that means that it's that 2 pi r means that, which is the diameter of the Earth would then be 8,000 miles based on that, because it's the circumference divided by pi, and we kind of know it's 24,000 miles around the Earth, because it's kind of like the 24 time zones. We know it's about 1,000 miles per time zone. We can kind of estimate that even from knowing about the US. US is about 3 time zones, and so on. So then, okay, so we've worked out then that the radius, is that right? The radius would be 4,000 miles, and then the volume of the Earth will be 4/3 pi r cubed, which is 4,000 miles times, let's see. I'm pretty bad at this mental arithmetic. It's like 5 times the cube of 4,000. The cube of 4,000 is, 4 cubed is 64. Let's see, 1,000 would be 10 to the 3, 10 to the 9. 64 times 10 to the 9, and let's say times 5 would be about 10 to the 11. So that would be 10 to the 11 cubic miles for the volume of the Earth. Okay, so that if that's the volume of the Earth, then each cubic mile is about, well, it's about it's 1760 yards in a mile, if I remember right. This is a terrible memory exercise for me. You know, you can just type this into Wolfram Alpha and see what the answer is. Maybe I should just do that, just to actually get it right. But let's keep doing the mental arithmetic, okay? Just see whether we can get it right. So it's 10 to the 11 cubic miles, and it's each cubic mile is each cubic mile is, let's say, 2,000 meters on a side. So that's 2,000 meters is cube of that is 10 to the 9 times, so that'd be 10 to the 10 cubic meters per cubic mile. So that's 10 to the 11 cubic miles times 10 to the 10 cubic meters per cubic mile. That's 10 to the 21 cubic meters. So that's our estimate for the volume of the Earth, 10 to the 21 cubic meters. And then the next thing we need to know is, if we're trying to work out the mass of the Earth, what's the density of the Earth? So the density of water is 1 gram per cubic centimeter. The density of rock is about 5 grams per cubic centimeter. And so that means that is per cubic meter. So if it's 5 grams per cubic centimeter, that means each cubic centimeter is 1/100th of a meter on the side. So that means it's so there's 100 centimeters going into 1 meter. So 100 cubed is 10 to the 6. So that's 5 times 10 to the 6 grams. And in kilograms, that will be 5,000 kilograms. So that's 5,000 kilograms times 10 to the 21 would be 5,000 kilograms times 10 to the 21 would be 10 to the 24, 5 times 10 to the 24. So our estimate based on this terrible mental arithmetic is 5 times 10 to the 24 kilograms for the mass of the Earth. And now I have to go just use Wolfram Alpha and type in mass of the Earth. And let's see how far off I am. Oh my gosh, 6 times 10 to the 24 kilograms. We win. Cool. All right, I'm impressed that I can still do any kind of mental arithmetic. I have to say, as a matter of educational history, I was always, when I was a kid, I was always just wretched at at remembering things like multiplication tables. And I gradually, over the course of my life, I have a decent memory, as maybe you can tell from these live streams. I've gradually filled in different multiplication facts. But for example, in that piece of mental arithmetic that we just had to do, which I'm very proud of having gotten more or less right, most of what we were doing was adding things and the occasional multiplication, but it was only an approximate multiplication, and we didn't need to remember that 7 times 8 was 56. That was the one multiplication fact that I learned when I was 7 years old, I think, because it was the one multiplication fact other people could never remember. So I always sort of came out ahead by just knowing that one fact. But in any case, let's see. Well, so the question was, that was the question of how much does the Earth weigh? So we've learned it's 5 times 10 to 24 kilograms. And by the way, yeah, so now the question was, how much does the sky weigh? More tricky. So let's imagine that we were to take, let's see how to work this out. The question is, if we took all the gas that's in the atmosphere and put it in a box, how much would that box weigh? So let's see how we would work that out. What do we know? We know the pressure. You know, this might be a R-square from alpha. I'm just going to say maths of Earth's atmosphere. Let's see if we actually know it. I think we could, oh yes, we do. 5 times 10 to the 18 kilograms. So that means that that's kind of interesting. That is telling us that the mass of the atmosphere is about 1/millionth the mass of the Earth. So 1/millionth of the mass of the solid Earth, 1/millionth is the gas that's in the atmosphere. It's kind of an interesting number, actually. And I wonder how that, for other planets, I wonder whether there's an easy piece of scaling that you can do. So for example, for Mars, the atmosphere, I wonder whether we know what the mass of Mars's atmosphere is. Let me see. Oh, yes. 10 to the 16 kilograms. So now I'm curious, if we work out the mass of Mars's atmosphere divided by mass of Mars itself, I guess it's going to be significantly smaller than, let's see, mass of Mars atmosphere. Let me see. Can we work this out? Oh, very strange. It's not telling us the answer to that. That's odd. Oh, I see. I see. It was confused. Okay, it's 4 times 10 to the minus 8. So it's about, so that means that in the case of Mars, the atmosphere is a smaller fraction of the mass of the whole planet than it is on Earth. It's roughly 60 times smaller for Mars. The atmosphere is a 60 times smaller fraction of the total mass than it is on Earth. Now for Jupiter, it goes the other way around. For Jupiter, it's kind of all atmosphere, no solid thing. There's probably a solid core to Jupiter right at the center, but it's mostly sort of all atmosphere and all gas. So I'm going to make the guess that as you look at, well, for smaller planets, smaller things like the moon or even like Mercury, the thing that all of the gas will have escaped. I'm now curious about Venus and whether in the case of Venus, oh, fascinating. Okay. So for Venus, the mass of the atmosphere is almost the same as it is for no, actually it's 10 times larger. No, 100 times larger than the mass relative to the mass of the planet as it is on Earth. Okay, so my potential hypothesis that as the mass of the planet gets higher, the fraction of the mass that is in the atmosphere goes up doesn't seem to be correct, based on the fact that the ratio of mass for Venus compared to the Earth differs by a factor of 100. So in any case, but we did find out that the atmosphere weighs about 1/millionth the mass of the Earth. And I say weighs in this rather vague way because, as I said, as I explained, what really is the thing you can compute is the mass, not the weight as in being pulled by the gravity of the Earth. Let's see. Jamie asks, what would happen if gravity on the Earth suddenly changed to the gravity of the moon? What if gravity suddenly got stronger? Well, I mean, so many things would change And it's one of those things where in physics, so many things are connected. You can't just say, let's just change this one parameter, change this dial, and see what happens, and expect everything else to remain constant. There was a theory due to a well-known physicist called Paul Dirac originally, that perhaps some of the fundamental constants of nature might have changed over the course of the time that the universe has been around. In particular, the so-called fine structure constant, which characterizes the, essentially I think in his theory, the gravitational constant, the thing that characterizes the strength of gravity. Given two masses of a certain size, how much force of gravity will there be between them? It's possible that that quantity could have changed in the history of the universe. I don't think it has, and in our theory of physics, that's not something you would see happen, but you could imagine a theory of physics in which the gravitational constant changes, and that would effectively have the result of changing the force of gravity. And people have worked out a little bit of what just changing that knob would do to what happens in the universe. So, for example, it certainly affects greatly the expansion of the universe to change the force of gravity over time. It also affects the Earth. As I recall, the Earth, the distance between the Earth and the sun changes. I think for some reason the Earth itself expands as a result of probably a fixed pressure from the inside of the Earth and a reduced gravity pulling the Earth together, so to speak. So a bunch of changes like that. And I think there are attempts to kind of map out the length of the day has been gradually getting longer. Days on the Earth, the time that the Earth took the Earth to spin on its axis was shorter back in the past. And this effect of changing gravitational constant would change that even more. And I think there have been attempts to kind of figure out whether you could detect a change of the gravitational constant from that. But it's really hard to say what happens to things when you just change one parameter in physics and not others. They tend to be all very connected. Let's see. Let's see, a couple of questions here. So I see KM asking, a full data memory card versus an empty data memory card of the same kind, will there be a difference in weight of those two objects due to the filling of that data? It depends on how the data is encoded. I think, let me give a couple of examples. Probably the answer in that particular case is no for a modern memory card, because, well, and this may depend on whether it's dynamic RAM or static RAM, all kinds of details. But, well, let me think about that for a second. I mean, essentially, what one's dealing with is there's no difference in the number of electrons that exist in the material. So it's not like there are more electrons. In the case of modern semiconductor memories, it's not like there are more electrons there than there would otherwise be. But there is a different state of motion of those electrons in certain cases, and that might be a way you would encode a bit. The presence of a bit might be the presence of electrons moving, circulating in some way, as opposed to not. I mean, it's not like when people would count by collecting pebbles or something, where there's a pebble to represent a 1, or there's no pebble representing nothing. Instead, the effect is a very subtle one to do with potentially the motion of electrons rather than them not being in motion. So now you might ask the question, if there are electrons in motion versus electrons at rest, would that affect the mass of the object? And the answer is yes, because let me see. I think the answer is yes. Yes, I think the answer is yes. I think the point is that that motion is that motion is associated with the electrons having a higher energy than they would otherwise have. In fact, in general, in a semiconductor, for example, when an electron can move from one place to another, it does so by increasing its energy to the point where it can kind of jump over the kind of barriers in the material to reach this conduction band where it can kind of move freely. And that requires that the energy of the electron be higher. So I think the answer would be that there will be a tiny effect of that, that the presence of a 1 bit probably would, again, it's a subtle thing. Okay, the fact that there's an electron in motion as opposed to not in motion could have the effect of producing a higher mass for the object. By how much? Well, we can work it out a little bit, perhaps. The band gap of silicon is 6 volts, which means that the electron is going, when it's kind of just sitting, at an atom, just hanging out in that atom, as opposed to promoted into the conduction band where it can kind of move freely. It's kind of has to have an additional energy of 6 electron volts. But the mass of an electron is about 500,000 electron volts. So that means that change of energy is, let's see, am I getting this right? Let me go to c squared. Yeah, I think I'm getting that right. If I'm not off by a speed of light squared, which will be embarrassing. Doesn't seem quite right. I think there's another factor, big factor actually. Yes, there's a factor of well, in any case, you can work out. I think there's a factor of 10 to the 16 that 10 to the 17 that I'm missing. I'm pretty sure there's that factor, which means that the effect of the sort of the electron able to moving around as opposed to being stuck in one place is I think an effect on the mass of about 1 quadrillionth of the mass, 1 million trillionth of the mass. So it's a pretty small effect, but there's another piece that probably makes this whole effect essentially zero, and it's the following thing. So you might say, well, when there's a 1 bit that you're storing, let's have the electron be circulating in the case to represent a 1, and if there's a 0, let's have the electron just be sitting there, not circulating. Back in very early computer memories, people did things like that. For example, some of the earliest computer memories were mercury delay lines, where you literally put a pulse of sound into the mercury. So you've got a compression wave into the mercury, and it would circulate around, and you would remember things by the fact that it took a while for the sound wave to circulate around, and you keep on amplifying it every time it came around. And so the presence of a compression wave was the presence of a 1, and the lack of a compression wave was a 0. So there was a definite thing that was different between the 1 and the 0. Similarly, when ferrite core memory was a thing, that was what the very first computer I used had. Those are little tiny pieces of iron, well, actually ferrite, iron-like material, where there either was magnetization in a particular direction or there wasn't magnetization in that direction. And the bits were, a 1 bit was stored by the presence of magnetization rather than the absence of magnetization. However, it turns out that's not a very electronically good thing to do, to say it's a 1 if there's something there, it's a 0 if there's nothing there. Better is to encode what you're doing in such a way that you use essentially a mathematical method to say, I'm going to take this sequence 1 0 1 1 0, for example, and have that represent the presence of a series of 1s, and have some other sequence of 1s and 0s represent a bunch of 0s. A common method is to use things called feedback shift register sequences as a way to encode to basically convert from something where to something where the number of 1s and 0s is always balanced. And so I kind of suspect that many memories are doing that. And that means that this whole sort of counting how many times there's a 1 versus a 0 that won't really be a thing. And it's something where there won't really be a difference of energy between, oh, it's all ones versus it's all zeros. But these are, I mean, there are a lot of cases where one tries to, for example, do computer security hacks by looking at, oh, the thing will use a tiny bit more power if it goes in that direction versus that direction, and using that to kind of be able to tease out what's going on in the chip, even when you didn't, when you sort of weren't supposed to know that. Anyway, you're asking difficult questions. You guys are asking difficult questions today. Let's see. Stephen asks, do brains like ants and so on and bacteria have brains? Assuming they do they have emotions? Do they feel pain? In the case of bacteria, which don't have a brain, what governs their behavior? Well, things like ants do have brains. We have about 100 billion nerve cells in our brains. Ants have about 50,000 in their brains. So ants have much smaller brains than we do, but the stuff in their brains is very similar to the stuff in human brains. It's a network of neurons, and which are electrically affecting each other and have pretty much the same biochemistry as human brains have. Now, the question was asked, do they have emotions? I think emotions are probably the result of kind of a general kind of sea of neurotransmitter, something like serotonin, dopamine, something like this, some chemical that kind of washes over human brains and causes one to have some emotional state. Probably that's right. Probably it's not something where it's the individual firings of individual neurons. It's rather a more collective effect that kind of bathes the brain in some particular chemical that leads it to have a general overall kind of predisposition to be happy or sad or whatever else it is. And that sort of general bathing in that neurotransmitter affects the individual firings of particular neurons by tipping them just a little bit in one direction versus another. So does that effect happen in things like ants? My guess is yes. I think they have the same neurotransmitters that we do, more or less. And my guess is that there are, I don't know whether anybody's ever measured it, there will be the same kind of overall change. In human brains, something that you can often detect is, well, you can certainly detect it, is the EEG signal. That is the sort of while each individual one of those 100 billion neurons is kind of firing in response to another neuron firing, and there's a little electrical pulse and so on, there's an overall collective kind of wave of electrical activity in the brain. When you're awake, it has one particular form. When you go to sleep, it has a different form, and so on. It's pretty hard to interpret in detail, and people care a lot because, for example, things like epilepsy are the result of kind of that going out of control. Or at least epilepsy, in epilepsy, that goes out of control. What's cause, what's effect is not so clear. But in any case, the thing that you can ask, I believe ants and things like that do have a small EEG signal, but EEG is not generally related to emotional states. It's just something that is kind of a collective aspect. For example, you can tell, you can have some idea of whether things sleep based on looking at different kinds of EEGs. And so, for example, fish are known to sleep in some sense, and you can detect that by looking at their EEG. I don't think that ants sleep. I don't think they have the same sort of very different kinds of EEG signals that we have, for example, when we're awake versus asleep. But so I'm sort of guessing that ants have some proxy for emotional state based on neurotransmitters in their brains and so on. When you go to lower organisms, well, for example, one that's very well studied is a nematode C. elegans that has it's a little critter with about, how many is it? I think it's a couple of thousand cells. And it's one thing about an organism that small is it's kind of genetically determined where every single cell goes. For us, there's sort of a general outline of, oh, we're going to have the cells that make fingers and eyes and brains and things like this. But the details of where each individual cell goes in our bodies is not determined genetically. It's just the overall pattern that's determined. For something like a nematode, one of these C. elegans critters, sort of the position of every single neuron is every single cell is determined. Now, in that organism, there are a bunch of nerve cells. There are hundreds of nerve cells, and the precise circuit of connection between those nerve cells is known. And so you can do things like you can see, what is the effect of stimulating the front of the critter, and does that cause it to contract some muscle-like thing at the back of the critter, things like this. And so there's a lot that's known about how that works. And for example, there are, well, I certainly remember in a creature called aplasia, which I think is very similar to the C. elegans, you can see learning happening. You can see individual connections between nerve cells getting strengthened by the experiences the organism has, or getting reduced in intensity by the experiences the organism has. So in that sense, these things, while they only have hundreds of nerve cells with a very definite sort of circuit, there's still something that's a bit like a brain, and where there is the possibility of individual neuron learning. And what we've kind of learned from the success of artificial neural nets in doing a lot of human-like tasks is that it really does seem that this idea of learning by changing the strengths of weights between nerve cells does seem to be something that is an adequate explanation of what's going on in even things like human brains. Now, when you go down to things like bacteria, they're just single-celled organisms, and bacteria don't have kind of the opportunity to have sort of electrical signal type brains in the same way that we do, with lots of different nerve cells and reactions between those nerve cells. But it's still the case that bacteria can do things where they sense their environment and they have a reaction to their environment. So a very common kind of thing is the following, that you'll have a little, there'll be some environment it's in, maybe it has a lot of sugar, maybe it has not so much sugar in the environment, and maybe the critter wants to find sugar. So if it's in a low sugar environment, it wants to just keep going in a straight line. Like maybe it's an organism that has little flagella that are like little sort of things that wiggle to make the thing move. And so what it might do is, if it's in an area where there's not much sugar, it just wants to keep going in a straight line in the hopes that it will get to another area where there might be more sugar. But if it's in an area where there's lots of sugar, it's really pretty happy to just stay where it is and not move around. But nevertheless, the way it works is it's always got to be running these flagella. They were always keeping on sort of like little millipede feet or something, keeping on going. And so a strategy it can use is, if it's in a place where there is, where it's happily got lots of sugar, it'll kind of keep randomly spinning around. So it won't keep in a consistent direction. It'll spin itself around, and so it'll sort of randomly walk around and not kind of systematically go out of that region. But if it's lower sugar, it will stop spinning around so much and it will just keep going in a straight line. So the ability to do something like that is a very sort of biochemically determined thing. I don't remember the exact signaling pathway for that one, but essentially the presence of one chemical leads to some other chemical being produced inside the bacterium, which then leads to the thing that leads to activity of the flagella that move the thing around, or whatever else it is. That's kind of a way in which an organism like that can essentially react to its environment. And it's not within an individual organism. The organism doesn't learn, but what will happen in that case is that there will be sort of evolution happening when this organism, every half an hour or something, maybe the organism will split in two, and that'll make two copies of it. There'll be two organisms, then four, then eight, and so on. And depending on what the environment is like. Every time that division happens, there'll be a small change. There'll be little random errors that get made as the genetic material gets replicated. And then, so some of those bacteria will gradually be slightly different. And what will tend to happen is the bacteria that are better suited to the environment that the thing is in, those will replicate a little bit faster, they'll replicate a little bit more. And so there'll be more of those bacteria. And so gradually it will be as if this sort of whole population of bacteria is learning, because there'll be a sort of a better bacterium that's produced that will be the common thing that's produced. But I think so that's sort of behavior within an organism is determined biochemically. Behavior of a population of organisms tends to be determined by things like natural selection and evolution. There are some weird cases, like there are some things called slime molds that are kind of these organisms that a collection of cells that form themselves into very elaborate shapes. And they do that by that they're just molecules that signal between those different cells, and that cause the cells to arrange themselves in different ways. You know, there are other things. There may be some electrical phenomena that happen even in things like bacteria. I think that's not really very well understood. And certainly there is some, in the way that biochemistry works, there is transport of both atoms and electrons. And whenever there's transport of electrons, it's kind of like there's an electrical signal, but it's not like there's kind of a great big wire. It's an electron is being passed from one molecule to another in a very, very definite way. I mean, that's something that happens in many places in biology. Sort of what's really going on is there's this sort of extra electron that got passed from one molecule to another and so on. Let's see. Oh boy, you guys ask hard questions. Paula is asking, how was it discovered that caffeine could energize us? Do all living things experience these effects, or is it exclusive to humans? I don't know when coffee was discovered. I'm going to guess that it's a new world thing, and it might have been known, I don't know, it probably was written down, I'm thinking in the 1500s or something, but I'm not sure. I think on the theory that people tried eating almost everything and saw what effect it had, that was probably something quickly discovered. But I think this question of whether something like coffee has caffeine, has what effect it has on our brains versus what effect it has on other brains. I think it has an effect on lots of kinds of brains. So for example, I know there are experiments where you take a spider that's weaving its web and you give it caffeine, for example, and it'll go kind of hyperactive and it'll start weaving its web in some crazy, different, not very well organized way. So at least a spider brain, which I'm guessing is kind of comparable to an ant brain and maybe 50,000 neurons or so, that seems to be affected chemically in that same way. And my guess is that it's something similar to, you're kind of just changing the characteristics of how every nerve cell produces its electrical signals and so on. And so it's going to have an effect at a very basic level to sort of anything that has nerve cells. That would be my guess. Let's see. Fortuitous asks, if electronics have coils and the brain has coils, should we be more conscious of signals like radio signals and so on? Oh, this is a giant can of worms. So one of the questions is, in the modern environment, there's all kinds of radio signals all over the place. And there's been sort of a consistent belief that radio signals, at least at the intensities that they typically are used for communicating between devices and so on, really don't have biological effects. Now, if you have an intense enough radio signal, it absolutely has a biological effect. A microwave oven is an intense radio signal, typically tuned to the frequency of the rotational band of water, which means the microwave oven is sort of putting electromagnetic energy into things like food and taking every water molecule in there and making it spin around very rapidly. And then that spinning around gets transferred into just heat of molecules moving around in your food. That's why if you put ice in a microwave oven, it doesn't work so well, because it's not able to take like a water molecule and start spinning it around because it's locked in the ice cube. But in any case, in a microwave oven, you're dealing with just essentially radio waves, but they're intense enough, sort of enclosed in that cavity that makes the microwave oven and amplified up. They're intense enough that you cook food and things like this. And you could imagine that, well, you would unfortunately cook yourself if you put yourself in a microwave oven. And there are even various weapons that have been tried to be built, I'm not sure how successfully, of directed microwave weapons that will produce intense microwave beams that will sort of cook anything in its path, so to speak. So we know that at the level of high intensity, you absolutely can have biological effects from electromagnetic waves, from radio type waves. Now the question is, when you get down to the 2 milliwatts, I think. 2 watts, is that right? Oh gosh, I'm forgetting what the standard is for cell phones. But when you get down to the intensity of radio energy from a cell phone, can that have an effect? Can you be sensitive to that? I mean, in the environment that we're in, there's lots of radio energy that's in most places. I mean, there are cell phones, the cell phones are regularly communicating. Even if you're not talking on your cell phone, it's regularly doing little handshakes, communicating with a cell phone tower to sort of check in and so on. Then, Wi-Fi, communication between computers, there's continually things being sent back and forth. And then even electrical wires have 60 cycles per second of alternating current electricity, and that produces a very low frequency electromagnetic wave, a kind of hum, if you were to play it on a speaker, so to speak. But that's another source of electromagnetic radiation. And there's lots of sources in the typical environment that we find ourselves in, with lots of devices and so on. And so it's been a long-running argument. Can that have a biological effect or not? And for example, you hold your cell phone up to your head, is the electromagnetic radiation that's being produced as the cell phone tries to transmit radio signals back to the cell phone tower, is that radio energy having an effect on you and your brain and so on, or not? I think the main conclusion is, if there's an effect, it's not a dramatic one. There have been lots of studies done of whether people, get more tumors when they use cell phones and hold them up to their heads and so on. And the answer seems to be probably not. I think those studies are always very hard because there's a lot of kind of vested interests in people want to use cell phones. Companies that make cell phones and so on want cell phones to be used. So it's a high bar to say, oh, there's something terrible about these things. People shouldn't use them. I mean, I have to say, personally, I tend to avoid kind of holding a cell phone up to my head more than I have to, and I tend to just use a headset and so on, just because I don't think it's definitively clear that there's no sort of cooking of the brain, so to speak, that happens as a result of that electromagnetic energy. There's a lot of controversy about what's actually even been found in regard to those kinds of things. And one of the things people have certainly noticed is that there are molecules that have kind of helical structures and so on. That's a very common motif in proteins, to have so-called alpha helices, where pieces of the protein were made mostly of proteins, where there's sort of pieces of the protein that are arranged in a kind of helical pattern. And that helical pattern is kind of like a tiny, you can think of it like a tiny antenna, if there's electromagnetic energy there, you can end up with something where, yes, it will make the electrons in that helix, it will push them a little bit around that helix. And that's a little bit like what happens in a typical radio antenna. Does that have an effect? I don't think we know. Could it have an effect? Well, yes, potentially. But the effect might be so infinitesimally small as to be irrelevant. It could be that yes, there's an effect of the the radio energy from the cell phone, but there's a lot more effect if you put your hand on your head or something, that has a bigger effect because the effect is so tiny. I don't think we know. So it is the case that cell phones do tend to adjust the amount of energy that they're putting out based on whether they think you're holding them up to your head or even holding them at all. And there's a whole elaborate protocol for sensing the fact that a hand is holding a cell phone and what that means in terms of the intensity of radiation that's being produced and so on. And in an attempt to kind of, if there is a biological effect, to prevent it being so dramatic. But I think the question is, I suppose, can people can people sense the presence of electromagnetic radiation in some way in the brain? And the answer is that it's complicated. There's not a lot of evidence that they can, but there are some limiting cases where they can. For example, I don't know this as a very good scientific fact, but I know 40 years ago or something, when I was interested in experiments in particle physics, and experiments in particle physics often involve having huge magnets that are intended to deflect particles so you can tell what the charge of the particle was, things like that. And the question was, if you just hang out, if you walk inside one of these big magnets, can you tell you're inside a big magnet or not? And people always used to say that you got a funny taste in your mouth when there was a big magnetic field. It's possible. There's certainly some electrochemistry that happens in taste that could be affected by that. I don't think that happens when people get MRIs, for example, which also involve high magnetic fields, although maybe not as high as those particle physics experiments. So that's kind of a point against that kind of detection. Now, I also mentioned the case of pigeons, where it's believed that pigeons sense the magnetic field of the Earth, which is really weak, 1,000,000 times weaker than the magnetic field in an MRI machine or something like this. The thing that it's believed that the most likely thing is that there are sort of individual atoms whose orientation is basically affected by the magnetic field of the Earth, and there are things in the brains of pigeons that sense those. Well, if pigeons have them, we might have them too, and that might mean we could sense electromagnetic fields. I don't know. I have to say, I personally, to say something absolutely weird about myself, had long had the experience that if I handle strong magnets, my fingers tingle. I don't know why. I don't know whether that's really a real effect or not. I have to say I've not done good experiments on it. My children at one point tried to do some experiments on me and claimed that the results were deeply inconclusive, but I'm not sure. And but it's certainly something where I really haven't looked into it adequately, and I haven't done the adequate experiments, but something where I certainly wondered, can the presence of like a rare earth magnet or something, and as you move the rare earth magnet around, it will induce electric fields in your fingers, and can you sense those things? And maybe yes, I don't know. I think this is it's an area where things are not well understood or well known. And I think this whole question of sort of the biological effects of magnetic fields, small amounts of radio energy, those kinds of things, not really very well known. As I say, if you have enough radio energy, it'll cook things. So that then it's very clear what happens. That there are, but it's a It's one of those things that's currently unclear, and people might worry that, well, something that's changed in the world is that, well, now we have lots of radio things bouncing around, and that might have some biological effect. People wonder, for example, about 5G, where actually I think that the way that 5G works, it's very inefficient to have a signal going from your cell phone and sort of going out in all directions to get to a cell phone tower. One of the things about 5G is attempting to arrange things so that the signal only goes in a very particular direction. So in the end, that probably means, unless you happen to be always in where the signal is going, so to speak, that probably means there's less radio energy concentrated in some particular area than there would be with earlier kinds of radio technologies, because basically the way that you optimize things is always to just have the signal go from the place where it's being transmitted to the place where it's being received, and not to just spread out in all directions and only a tiny bit of it happens to go in the right direction. But that it goes out in all directions and only a tiny bit goes in the right direction, that's the sort of traditional way that radio works. You have to do much more elaborate things, so-called phased arrays, where you're basically having multiple pieces of an antenna, and the pieces of the antenna are kind of producing radio waves in such a way that the phases of those radio waves interfere so that you concentrate all the energy in a particular direction. That's kind of the idea there. So somebody is commenting that yes, the cell phones go up there 2 watts. That's right. That's the standard number, and I think they usually operate, when you're holding them, they think they operate usually about ½ a watt. It's always an interesting challenge when, if you're just at the edge of where cell phone reception is a real thing, you know, can you improve the cell phone reception by sort of attaching yourself as an antenna, so to speak, to the cell phone? And usually most cell phones, the antenna kind of goes, well, they're different patterns, but a common thing is to have the outer case of the cell phone be part of the antenna. And so, you know, you can actually, by holding the thing, you can make some level of electrical connection to it, and you can potentially be sort of part of the antenna or not. And I have to say, let's see, maybe one more question here. Jamie is asking, is there a reason for food likes and dislikes that each person experiences? Can taste buds be tricked? Well, the taste buds are really complicated things. They, in the end, taste, like smell, is presumably associated with the way that particular molecules in food, particular molecules sort of arrange themselves on molecules that are in taste buds or whatever else. And so what happens is, you know, the food gets kind of crushed up, and it gets mixed in with saliva and so on, and partly dissolved and all these kinds of things. And then in the end, it's okay, the food has a certain shape of molecule, and the taste bud has a whole arrangement of different kinds of molecules in it, each of which has a different shape. And presumably what's happening is, the biggest effect is, well, does the shape of one molecule align with the shape of another molecule? Do these things stick together? If they do stick together, then the result of that is eventually to produce a nerve signal, to make a nerve cell fire, and that nerve cell, the electrical effect from that nerve cell goes to your brain, and you say, oh, I'm tasting something. Well, there are some things that are known. So for example, it presumably is the case that the actual molecules that occur in those taste buds and the shapes of those molecules are determined by the whole sort of genetic plan for the organism. And so there are particular things known, oh gosh, what are they? They're things like whether some foods taste bitter or not. Maybe asparagus maybe is one of, I'm not sure. There's some certain herbs that taste bitter to some people and not to others. And it's known that there's a genetic kind of correlate of those things. That is, people whose genome has a particular sequence in a particular place they'll make a particular protein. The protein will be a particular shape. That particular shape will or won't fit in with that particular kind of plant or whatever it is, or the proteins that exist in that particular kind of plant. And so some set of people will genetically tend to like that kind of food, or that kind of food will taste bitter, or whatever else. And it's always amusing to, I know with my kids, for example, that they have definite preferences in food that seem to be, even with sort of blind experimentation, seem to be similar to ones that I have. And so that's presumably, or maybe that's a nurture phenomenon of those were things that were around when they were growing up. But I think there's enough different cases of this that that's probably not true, and that it really is a genetic predisposition to like raspberries or something like this. And that presumably comes because the actual sort of shapes of molecules that exist in taste buds, which are genetically determined, run in families and so on like that. Now, in terms of what things that taste good versus don't taste good, it's always amazing that the sort of details of how food is presented and how it's been crushed up, and whether it's got a big surface area or not, or whether it's in little tiny particles or not, or how it's mixed with other things, those have big effects on the perception of taste. And I also tend to think that, when people talk about such and such a thing as an acquired taste, there's some process by which we can kind of get used to a particular taste and start to, quotes, like it. And it's maybe not a thing where we are necessarily, born liking this or not liking that. I know in the course of my life, there are things where I really didn't like them back 50 years ago, and I've come to find them really pretty good foods in later years. And so it's sort of a thing which can definitely change. Now, I think that there are sort of things that come with the species of things we tend to like we tend to like sweet things. And well, why is that? I mean, we can answer that at a couple of levels. I think one is that the question of sort of how our brain is wired up to respond to different kinds of things, there's a certain amount of the wiring of the brain that's been determined by evolution, and presumably some of that wiring is set up so that the wiring we got is the wiring that's been evolutionarily more successful. So, for example, wiring that says kind of walk right off a cliff is probably wiring that is not going to survive evolutionarily, because if everybody with that wiring walks off a cliff, they won't have kids, and they won't have kids who inherit that tendency to walk off a cliff. And so similarly, it tends to be the case. For example, sweet things are good sources. Glucose is what gives us energy and things like that. So, well, part of it at least. Those are things that are sort of have a positive effect on us when we eat them in some sense. They quickly give us energy. So if if we have to figure out, we're going to run away from the mammoth or something like this. It's a good thing to have eaten some glucose when we're running away from the mammoth. So the folks who learnt, it's a good thing to eat glucose and liked eating glucose will be ones who will be more successful in running away from the mammoth. And therefore, they'll be the ones that have more children and things like this. And so that will become a trait that gets burnt into the species. So I think that's but this whole question of I think this question of what we like and what we don't like, it's probably also correlated with sort of our whole set of experiences. Like, it can probably matter what the packaging of the food is, whether there's food coloring that makes the food some horrible color versus some really attractive color. Those things probably all have an effect. And we probably learn from the fact that, we think that's a really nice color of candy or something like this. And we then say that's a nice color of candy. Then we taste it. Then we associate that taste with, we like that thing. and then pretty soon we like the taste of that thing. So I think it's a complicated collection of connections. I do think that, I don't know when it comes to, for example, kids who say, I don't like food X or Y. I was certainly one of those kids. Some of my kids have been of that type too. And one of the embarrassing things for me is some of the things where I said, I don't like that and refused to eat it when I was a kid, are now really popular foods for me. And what happened? Did my sense of taste change, or did I just sort of learn different associations with that food? I'm really not sure. I think also another dynamic that happens is that our body is pretty good at sensing what we need, so to speak. And so, you'll have, the craving for this or that kind of food, and it'll be like there seems to be a feedback mechanism that seems to be of a chemical nature that says, oh, you haven't had enough of this, you need a food that has that kind of thing in it. You need more iron or something, you have you crave this kind of food. I'm not sure how well understood all those kinds of things are, but that's a mechanism by which we're kind of, our brains are connected to the things which are sensing the fact, oh yes, we ate food that has this or that in it, and then we either want more of it or we don't. All right, well, I should probably wrap up there. Thanks for a lot of questions, some of which were kind of difficult today. And look forward to doing this another time. And on what just a logistical point, on Fridays, I've been kind of alternating between doing this general Q&A about science and technology and doing Q&A about future of science and technology. And so next week, I think we'll be doing a future of science and technology Q&A. And I encourage people who are interested in getting questions answered, please send them on the submission forms that we have. And even if you don't have a chance to see this live stream live in real time, I think our system is such that if you leave your email address when you send in the question, we'll send you mail. If I got the chance to answer that question, you can check it out in the archive of the live stream. All right, well, thanks for joining me, and bye for now.